Good morning, everyone. So I'm Chong, and today I'll be presenting on this paper, Albert, a Lite BERT for self-supervised learning for language representations. So this is the brief structure of the sharing today. I'll be going through the motivations, we'll be looking at some related works, and then we'll look at Albert, the things that Albert does. Then we'll have a brief conclusion. Okay, so to start off, when we talk about natural language processing, right, we have some task, and then there's some text that we need to process. So this is an example from Squad. So the task is question answering. They take text from Wikipedia, and then they have some questions, and they ask human annotators to give the answers to these questions. So you can see that the text is here, and then they show the ground truth from 4 different human annotators. So in order for you to solve this task, you actually need to convert the text into something that the computer can understand, right? But when you put in text into a machine, it actually gives you some bunch of numbers. And so there's a problem. How do we convert the meaning of the word into something that the machine can understand? So we need to learn a numerical word representation. So in the recently there's been the use of transformer models. So you give in some inputs, and the model takes in the words, they convert it to the embeddings, and then they pass through encoder and decoder stack, and then they output some probabilities to solve the question. I'm not going to go very in depth into the transformer encoding, the transformer model, but this is just a brief background for what you need to know, because then this is the part that you're interested in for us, which is the word representations. Okay. So the important thing is that we look at BERT, which is one of the baselines for Albert. So BERT involves multiple transformer stacks. So you have the embeddings, the word embeddings here, and then you pass them through the transformer stacks, and then there's an output at the top. There's a lot of different ways of combining the transformer stacks, but BERT is one of the better performing ones. Yeah. Okay, so we take a closer look at BERT. So for BERT, there's 2 parts to using BERT to solve NLP task. So the first part is called pre-training, where they take 2 sentences that's not labeled, and they pass it through the BERT model, and they want to they calculate the loss using these 2 tasks: next sentence prediction and mask language model. So the next sentence prediction is trying to predict if the 2 sentences are going to be consecutive, and then the mask language model is going to be somewhere here, where before they put the words in the sentences into the model, they actually mask a portion of the inputs, and they want to predict the word that's being masked. Okay. So after you finish pre-training, you can use the same model for multiple different tasks. You have to do some fine-tuning. So let's say you want to do sentence classification, then you have to use the first token of the output, and you use that as the class labels, then you calculate your probabilities based on that. If you want to do question answering, you look at the ending span, and then you use that as your answer. Okay. So BERT's achieved a state-of-the-art performance on GLUE, which is General Language Understanding Evaluation. And as you can see, there's 2 different versions of BERT that's being shown here on the results table. So BERT base, which is a smaller model, and BERT large, which is a larger model. So we are done, right? You keep calm, and you train a larger model. That's it. Not exactly. There's 2 main problems with getting a larger model. So first thing is that there's a physical limitation of how much memory you can actually allocate in the machine for you to train. And the next thing is that there's some communications overhead. So if you have a lot of models, you need to a lot of parameters, you need to update the parameters. You're transferring a lot of data. So this is a proportion. This overhead is proportional to the number of parameters, and then it reduces the training speed. Okay. So there are some existing methods to solve the memory limitation problem. So you can parallelize your models, you can make the memory management more efficient, but there's not really a lot of work being done on how to resolve the communications overhead. So Albert is, the full name is a Lite BERT. So what do they mean by Lite is that they are going to try and reduce the parameters, number of parameters in the model by these two, factorized parameters and embeddings and cross-layer parameter sharing. So these two would address the two problems here. And the last one is sentence order prediction, which is supposed to help improve the performance of Albert. Okay, so now we're going to go in depth into each of the methods. So the first one is a factorized embedding parameterization. So this is the BERT model, right? And you can see that over here we have two embeddings. The first one is going to be the context-independent word embeddings. So these are just, when you have a word, you see a word, it translates one-to-one to a specific embedding. And then you have the context-dependent hidden embeddings. So this is after the transformers. When you go to the output, you have some embeddings that are supposed to be representative of the word at that point. So in the BERT model, the hidden size h of all these embeddings are equal to the sizes of the input embeddings, input word embeddings. So what Albert does is that it separates the embedding sizes. So they reduce the word embedding size, and they do this by doing a matrix factorization. So the input embeddings over here can have a smaller size, and then they project it to some larger hidden embedding before they continue on with the training. So this reduces the number of parameters that they need to use for the word embeddings. Okay. So over here they actually show some different levels of embedding sizes for fixed hidden size of 768. So for 768, if you use the BERT way, which is the hidden embedding size is the same as the word embedding size, is the last row of each section. So you can see that as you decrease the number of embeddings, decrease the size of embeddings, generally the performance decreases. So you see over here there's 82%, goes down to 81%, but the impact is not a lot. Like the performance decrease isn't a lot, and you reduce the number of parameters quite significantly. So for Albert, the final parameters that they chose is usually embedding size of 1 to 8, which is this one. Okay, so then we go on to the question of what is this not shared and shared, which is the next part. So Albert also does cross-layer parameter sharing. So for BERT, they have different parameters for each of the transformer stacks. Albert says that we actually don't need to separate out these parameters. We can share the parameters for all these stack layers, and then it will reduce the total number of parameters. And as a bonus, it also helps to stabilize the training because you're only updating one set of parameters. Okay, so again, we have some experiments. So they try sharing different things. So we're given the same embedding size, they have not shared at all, which is the original BERT model. They have a shared FFN, which is the fully feed-forward network, which is the transformer part. Shared attention, which is not the feed-forward, but just the attentions within the transformers. And all shared, which is everything is shared. So all shared decreases performance, which you would expect because there's a less capacity in the model. And the most performance loss comes from the feed-forward network sharing. So anytime you share the feed-forward network, the performance drops at least like 1%, given the same embedding size. But still, the authors chose to use the all-shared method, which is they take the performance loss because the training is a lot faster. You reduce the number of parameters by a lot. Okay, so the last thing that they do is sentence order prediction. So in BERT, you actually have a task called NSP, next sentence prediction. So what it does is that it's trying to predict if the two input sentences, A and B, are consecutive. Okay, so for example, let's say we have 3 sentences. SMU is the third autonomous university in Singapore, and you can read the rest yourself. And then you want to decide which sentence comes after the first sentence at the top. Okay, so NSP says that simple. We look at this sentence, this should be the correct answer. The university provides broad base, blah, blah, blah. And this is the wrong answer. So it doesn't flow. Okay. But what Albert says is that you don't actually predict the coherence. You're actually predicting the topic. So you're just saying that these two sentences share the same topic, and these two sentences do not share the same topic, which is a different. So the impact of the task is different from what the authors intended. So Albert suggests a different task called sentence order prediction. So for sentence order prediction, the correct example would be the top one and then the bottom one. So this would be a correct example. And then the reverse, if you take the bottom sentence and then the top sentence, as bottom sentence is A, top sentence is B, then it's going to be a wrong example, negative example. So this would allow the model to better understand the coherence between the two sentences, which is what the NSP is supposed to do. Okay, so moving on. They tried, so they showed the results of the experiment with no sentence prediction task, with NSP and with SOP. And SOP generally outperforms the NSP. Okay. So down to the conclusion. So Albert is achieving, so this is done on the books, corpus, and Wikipedia. So similar to BERT training. And they show that it's actually achieving state-of-the-art results for multiple NLP tasks. So you see BERTs over here, and then Albert, the different sizes. And oh, so one other thing that the authors mentioned after that was they actually used Dropout in the initial training, and they realized that Albert doesn't seem to overfit the training data at 1 million training steps. So they took the checkpoint at that over here at 1 million, and they actually train it without Dropout. So they remove Dropout and they continue training the model. So the intuition is that they, since the Albert is not overfitting to the trained data, so by removing Dropout, you increase the capacity of the model to learn, and then you can achieve better results as compared to if you use a Dropout. So over here, without Dropout, you get better accuracy. With Dropout, you don't get such a good accuracy. So after they did this experiment, they ran one last time on the glue dataset, glue benchmark, which is the same thing that BERT was using as a comparison. And yeah, they achieved good results with combined, this is the mass language model, and sentence order prediction task, and no dropout. Yeah, so that's the results here. Okay. So conclusion for deep learning versus the traditional approaches. It's still slower than the traditional approaches. So for you to learn all these representations, you have to take a lot of time to do the pre-training. You need a lot of data. But once someone has done the pre-training, you can grab the model if they release it, and then you can fine-tune it on your task, and that's a lot faster. And the deep learning approach is very effective. It is state-of-the-art for many NLP tasks. And even though it's a black box, right, literally a black box, you don't really need to explain, right, if you're always correct. So that's all. Any questions?